Hi, and welcome to our next section here in our chapter on regularization. So this is on Lasso Regression, so also called the L1 penalty. I guess maybe we can talk about the pronunciation of the thing first. So if I remember correctly, the two authors of the thing actually pronounce it differently. So you could stick with Mr. Tipshirani and call it the Lasso, or I guess you could pronounce it like Trevor Hasty, and I'm not exactly sure why I'm usually doing that, but I think I do. So he calls it the Lasso. So again, we'll want to, obviously study its algebraic form a little bit, understand the parameter shrinkage effects of the L1, but we also want to understand here already that the L1 penalty, especially in a linear model, can nicely be used to select features. So it's not only a countermeasure against overfitting, but it also enables you to do feature selection, especially in linear models. And we'll also talk a little bit about its support recovery property. What that exactly means, you will understand, I guess at the end of this video. Okay, let's start with its algebraic form. So if you've already seen the ridge, looks very similar in a certain sense, just using a different norm. So we're now using the L1 norm. So ridge, the L2 norm was I take every coefficient of my model, every theta j, I square them and I sum them up. So that's the squared L2 norm. I guess I sometimes might forget the square. And L1 is you take each coefficient, each theta j, you compute the absolute value and then you sum all of them up. Okay? So first of all, I think we could discuss a little bit what that means in terms of optimization. So we said for ridge, we can still solve it analytically. In a certain sense, the optimization even became, I didn't really discuss that, I think, in that video, but optimization for ridge actually becomes a little bit simpler because it becomes numerically more well-behaved through the regularization. For Lasso, actually becomes harder now. So before we just had a simple quadratic form, could solve that analytically. Now it's not even differentiable anymore, because we are adding in this non-differentiable component here. So it's still convex, but we can't even directly use things like gradient descent on this type of thing without at least worrying what happens because of the non-differentiability. But in this lecture here, I'll tend to talk a little bit less about the connection and the implications for optimization, so I'll leave it at that. Again, we are now looking at very simple examples as for the L2. Actually, I'm looking at pretty much the same examples here. So I'm using, again, this super simple data generating process, 3x1 minus 2x2, added in some Gaussian error. We know where the true parameter estimates are, and we now take a look at what happens if we regularize with L1. And for good comparison, I've copied over our visualization here for L2. So for L2, you can see that we just get pulled closer to the origin. And here again, watch out a little bit what the contour lines visualize. So for this, on this slide here, the contour lines are the unregularized objective. Okay, so the lost surface of our linear model. Now we can see for L2 that we get pulled back to the origin. For L1, something similar happens, but it's our path is now kind of taking a different path, right? And you can already see that something interesting happens here. At some point, we actually end up on an axis where theta 2 is exactly 0. So theta 2 and its associated feature now get pushed out of the model, and this is what I meant with this will help us to do feature selection, because we can drive coefficients and associated features completely out of the model, shrinking their associated parameter values to exactly 0 if we do L1. And this is our first indication that this happens, and we can exploit that in feature selection. Again here, different perspective. Now the contour lines change their meaning. So here I'm now visualizing the regularized objective, and in the top left corner, I'm starting with lambda equals 0, so it's actually the unregularized objective. And now I start increasing lambda to 1, to 2, and to 10. And here again, you can now see a little bit more clearly this mixing of the objectives, right? Where I start here with a quadratic form, so the risk, the loss of my unregularized linear model, I then mix in this non-differentiable part of the L1. And you can see how the objective now more and more changes shape when I mix in more of this L1 penalty component by driving up lambda more and more and more. And again, you can see in green where the true minimizer of the unregularized objective is and how the red point, the position, the minimizer of the regularized thing moves. And you can again see it moves closer to the origin. At the end, with the super high lambda value, we might even end up in the origin, but somewhere before, we very often end up with points where one of the coefficients or multiple of the coefficients, I don't have too many available to me in this 2D problem, become exactly 0. Here's another way of visualizing that in 3D. I guess I mainly included the plots because 3D it just looks a little bit more fancy and nicer. There's not a lot more to see here, so we can again visualize these regularized empirical risk surfaces for different lambda values, and we can see that we get these non-smooth kinks more for L1, which is here at the top, and not for L2, which is visualized at the bottom here. It's not more to see, I guess, in this 3D visualization. It's just, I guess, a slightly different way of looking at things. Again, varying and repeating something which we have done for the L2, we can now rewrite our regularized problem as with two components, the ERM part and the penalty part, as a constraint optimization problem. And the only thing that changes now is the geometry here of this feasible region. Before it was a ball, it was a circle. Because of the L2 norm, now we have the L1 norm, and we now end up with a diamond shape. So things like that. Again, we have this t value, the threshold, which controls the volume, the size of our feasible region. But more interestingly, because we now have these kinks, these corners in the feasible region, this actually enforces sparse solutions. Because the loss contours, they kind of have a higher likelihood to actually first hit these corners of the constraint region at the coordinate axes where some of the entries of our parameter vectors are 0. I mean, pretty obviously, so if you look at the coordinate axis like these corners here are located at points where one or multiple, in higher dimensional spaces, which I can't really visualize very nicely here, so where one or multiple coefficients are exactly 0. So of course this doesn't necessarily always have to happen, but it can happen. So this is usually what we mean when we say using the L1 penalty induces sparsity in our resulting vector. And I'll show quite a few more examples of this, so you can see this empirically, and I'll offer more theoretical, in-depth explanations that this really happens if you don't immediately or already believe this from this 2D visualization here. A few words on what actually happens. So I guess that's the first part of this more in-depth theoretical analysis. So we'll now analyze the L1 and the L2 penalty with what we call an orthonormal design. So that's a special case where x transpose times x, so our design matrix transpose times x is exactly the identity matrix. So usually that really doesn't happen in practice, but either you can see this as kind of a scenario we'll just explore for teaching matters, because it kind of simplifies matters a lot. I'll later study the non-orthonormal designs as well in a deep dive. Or you can also, I guess argue for looking at this, because you could do something like a Mahalanobis transformation on your original feature space, and then something like this here happens as well. So let's just assume that x transposed x is the identity now. So we'll now look at how our Lasso solution actually looks like as a transformation in terms of our, actually, we'll look at how our Lasso and our Ridge solutions look like as a function of the unregularized minimizer. So we'll see how Ridge and Lasso transform the unregularized solution. So for the Lasso, actually this thing happens here, okay? So we use on the OLS solution what is called the soft thresholding operator. So what we do is we pretty much use the parameters here from our OLS estimator, so the unregularized solution. We subtract lambda, so the complexity penalty, and we now do a capping at 0. So if the absolute value of theta is actually less than lambda, then this function will return 0. But if it's larger than lambda, we do this type of shrinkage here. Also multiply everything by the sign so that the sign actually stays. So I guess this might be easier to look at it by visualization. So maybe before we do that, let's talk a little bit about what happens with the Ridge estimator under this orthonormal design. That's really easy. I mean, maybe I skipped that a bit, but we could even look at what happens with the OLS estimator. So, well, we can just look at the normal equations, and then we see that x transpose x is in there. That becomes the identity. So the inverse of the identity is still the identity, and this is simply our solution here. This is now the simplified OLS solution under this orthonormal design. It's just x transpose times y. Now we can look at what happens with Ridge. So Ridge, formula looks very similar to the OLS, except for this plus lambda times the identity. So now x transpose x again becomes the identity. We can collapse terms a little bit here on the inside, and at the end you just get this here. So you see how your Ridge estimator is now transformed, is the transformation of the OLS estimator by a very simple transformation. So we just divide every entry, divide every estimated parameter value by 1 plus lambda. Okay, so the larger lambda becomes, the smaller, the smaller the resulting Ridge estimator under this transformation. So I've visualized this here below, where you can see in, what do we have here? So, okay, the plot you have to read in the following manner. So the idea is that what is on x1, so on this axis here, is your original parameter, and then on x2 is your transform parameter. So we could say what happens now under OLS? Well, nothing, right? So it's kind of the identity transformation. We don't do anything because the idea is that the input into the thing is the OLS parameter, right? So the dotted line would be the identity transformation, and that's OLS. Now what happens with Ridge? Something super simple. We divide everything by 1 plus lambda, right? So we end up with a line like that, right? So for a certain lambda value, I guess lambda was 3 here in this example. And this is the interesting thing, for Lasso, something more complicated happens because we actually apply this formula here, right? You apply this soft thresholding operator, and you can see that here there's this region where if the absolute value of lambda is quite small, the resulting transform value will be exactly 0. And outside of this, we do a little bit of shrinkage. And that happens under the orthonormal design. This soft thresholding actually still happens in a slightly more complicated way for non-orthonormal designs. And like I said, we'll look at this in a deep dive later. But the spirit of the analysis is still true for the more complicated and general scenarios. Okay, getting closer to the end of this session here. So again, here I've visualized full solution paths for L1 and L2. So here we have the contour lines. So on the right-hand side, we have L1. On the left-hand side, we have our friend L2. Again, I've visualized the contours here of the unregularized objectives of the linear model. I've visualized the feasible regions here. So balls and diamonds, left and right. And you can now see here the path that happens if I go from lambda 0 to lambda infinity. For L2, we looked at this before, but you can also look at it for L1. And again, you can see I move closer to the origin, but at some point I kind of end up on an axis, yeah, and parameters get shrunken to exactly 0. I've seen this now multiple times. Last but not least, and this is a more, I don't know, more informative, I guess, analysis on when does Lasso actually do the right thing. So when does it actually select the true support of our theta? So when are only the non-zero parameters found and recovered and estimated by Lasso? So we can formulate this as the so-called sign consistency property, where we want that the probability that the sign of theta hat, so the sign of our estimated coefficient, is exactly the same as the sign of the true coefficient, and that this goes to 1. So the probability that they are the same goes to 1 when sample size goes to infinity. Okay, and one way we can analyze that is by looking at a data generating process where we kind of consider a certain, I don't know, partition of our parameter space. So we now assume that there are like two parts, theta 1 and theta 2. So they are not scalars, they are like subvectors. That's like the first part of theta and the second part. And the true model is something linear, and it's made up of these two parts where we just have a design matrix as x1 corresponding to theta 1 and x2 corresponding to theta 2. So one way you can also visualize that is having your design matrix here made up of two parts, and then you multiply that with your vector theta, again made up of two parts. So yeah, this is exactly the same thing. Okay, now what we will assume is that there is actually just the theta 1 that's relevant, and that's non-zero in that model, and that theta 2 is actually 0. Yeah? So, of course, I mean, you can just ask, why do we include it if it doesn't matter? Well, because in estimation, we don't know, right? And we have these noise features in there from the theta 2 part, and it's a little bit unclear what happens with them under estimation with the Lasso, and this is exactly what we want to study here, right? So, what we can show now, and if you're interested into the details, you have to look into this paper, and I guess that one. So both are pretty nice to understand this support recovery property here more in depth. I can just summarize the results here a little bit. So what can be shown is that our estimator of the Lasso is sign consistent, so that this here is true if a certain irrepresentable condition holds, which is given here. So I don't want to read that out. The formula is not too complicated, but its interpretation is the following. So the Lasso is then sign consistent if the irrelevant features in this theta 2 x2 part not too correlated, if they're not easily representable, and this is why it's called irrepresentable theorem, by the informative features in the theta 1 part. Okay, if that is true, the Lasso will actually truly recover in estimation the structure and the part of the informative features. I'll leave it at that here. I hope you enjoyed it. Until now, see you in the next session.